Welcome up on the stage our first speaker, a true changer of engineering, Reynolds.
There you are. Good morning. We know you arrived late yesterday, so we thought we'd put you in tune with the conference context and some of the discussions. Yesterday we were discussing challenges, as Ulf mentioned, and this morning our first section is called Creative Chaos. We will look at some of the disruption that is taking place when innovation is causing systems to shift.
And also I think we've discussed how new business models have to be put in play and how new players have to come into this game.
Mm-hmm. And new ways of working, like we just heard.
Yes.
When collaborating, we cannot just bring our own interests. We need a common point of departure, a common vision, and a new leadership that can foster that kind of open culture. So that's where we are. How does this sound to you, Jesse?
Sounds wonderful.
Yes.
Okay,
all right.
Jesse. Engineering the climate and changing the climate in engineering. Could we?
That seems appropriate. That seems appropriate, yes.
Good. Great to have you here.
And
Right.
that's your time. You're
That's
25
my time.
minutes.
Awesome. Thank you.
And the clicker is right there.
All right. Thank you. Good morning. It's a genuine honor to be invited to speak here today. Thank you all especially for appearing at the first talk this morning. So I'll be speaking, as said, about climate change and about different ways in which climate risks can be managed and perhaps reduced as we move further into the 21st century, in particular ways in which engineering and related scientific fields can contribute to risk management. So I must apologize for the slide full of text. I promise this is the only one like this. The point being of this slide that climate change caused by our emissions of greenhouse gases, especially carbon dioxide, is causing and will continue to cause a wide variety of somewhat unpredictable environmental, social, economic, and political phenomena. Many of these effects will be negative. Most of them, if not all of them, have great degrees of uncertainty. So there's an inherent type of, at the very least, unpredictability moving into the future, perhaps even chaos. What motivates me personally is that in almost all these regards, the already vulnerable people on the planet, these are poor people in poor countries, are the ones who are most vulnerable. For better or for worse, those of us in relatively wealthy countries, especially at high latitudes such as Sweden, will probably be mostly okay. But what motivates me is the world's vulnerable. So I'm going to work through 4 general categories of responses to climate change. Now, the first logical approach is to look at the cause of climate change, which, as I mentioned, is our emissions of greenhouse gases, primarily but not exclusively carbon dioxide. This is a historical figure, estimates of carbon dioxide emissions in the world per year since 1850. And you can see that it accelerates, particularly since about 1950 or so after World War II. I'm going to zoom in on this, okay, since 1990. So here we are since 1990. This is because this is roughly the time when climate change was identified as a serious global problem. So the data is better. It also includes some space for the future. So the logical response, I'll hold off on that. The logical response, as I said, would be to reduce climate change. The logical response to try to reduce climate change would be to reduce greenhouse gas emissions. You probably know that there's been a series of international treaties to try to do so. There they are. Although there is no counterfactual, we don't have a world without these treaties, they do not provide clear chronological evidence of large effects on greenhouse gas emissions. The line keeps going up. That dip, by the way, is 2008 and 2009, the global economic recession. That reduces greenhouse gas emissions, at least temporarily. So because greenhouse gases accumulate in the atmosphere, in particular carbon dioxide that we add to the atmosphere stays there for hundreds of years, if we want to reduce climate change, if we want to prevent climate change, what we're concerned about is the area under the emissions curve, right? Because we're concerned about total emissions. So if we start thinking about how can we keep the area under this curve within a certain amount. For example, let's say we want to limit global warming to 2 degrees Celsius, which all countries of the world agreed on in the 2015 Paris Agreement. To have a good chance of doing so, we need to do something like that. If we were to assume a linear reduction, emissions need to go to 0 in around the year 2045. How might we do this? Is it feasible? Is it likely? Well, the Intergovernmental Panel on Climate Change is the authoritative international body for climate change assessment. They use 4 primary scenarios of the future, and this is their most optimistic one. And most informed observers look at this and say, this is not possible, this is too optimistic. Okay? Instead, we could turn to the Paris Agreement that I mentioned a moment ago in 2015. This works through each 5 years, all countries make commitments. What are they going to do? And if the first round of commitments are actually met, and there's quite a big if there, that's what emissions will look like, at least through 2030. Right now, we're on track to have only 2 countries in the world, Morocco and Ghana, meet their commitments from 2015. Most experts would say that emissions are going to rise much more steeply than the blue line. Probably, in fact, more steeply than they have in the past. So from this, I conclude that greenhouse gas emissions cuts cannot prevent dangerous climate change on their own. That's a hard truth. That's an unfortunate truth. Now, why is that? Why is that? Humans are pretty good at solving other problems, not perfectly so. I look at the problem structure. Who has what incentives? So greenhouse gas emissions cuts, now here I'm speaking of cuts, so it's in the negative, right? The reductions create net global benefits, more benefits than costs. But those benefits are spread out over the whole world, and the costs are borne locally. If some country were to institute or to raise a tax on carbon dioxide emissions, those costs are borne locally, but the benefits are spread out over the whole world and into the future. So typically, local benefits are less than the local costs. So this is called a collective action problem. If you've pursued a little bit of game theory, you'll be familiar with this. And the very predictable result is that the emissions reductions are and will remain very suboptimal. To make matters worse, to make matters even worse, the effects of greenhouse gas emissions or their reduction are delayed by approximately a generation, let's say, by 25 years or so, due to the need for the planet to reach new thermal equilibrium. So any benefits that accrue to a given country or other jurisdiction for cutting its emissions are delayed enough that it even further reduces politicians' incentives to do the hard but necessary work. Right? So what else could we do? Let's move on to option 2. Maybe we can adapt society and to some degree ecosystems to a changed climate. This is a complex process. It will have physical elements such as more resilient, more robust infrastructure, raising seawalls, perhaps relocating settlements to some degree. It also has social, political governance elements, such as systems that are more prepared for external shocks, particularly severe weather events. The good news, I suppose you could say, with adaptation is that such phenomena, such characteristics, should I say, are locally beneficial. They're also locally costly. So you have a better alignment of the incentives. So one can expect a certain degree of local optimality with adaptation, to some degree. Local optimality. But the problem is we live in a world of economic inequality. The capacity to adapt and the need to adapt are strongly inversely correlated. It's the poor countries that need to adapt the most because they're most vulnerable to climate change, but they have the least ability to do so. So you could say we're still going to have globally suboptimal adaptation, or perhaps a better way to put it is the distribution of adaptation will be highly suboptimal. In principle, the world could be improved by large wealth transfers to rich countries to poor countries, but we tend to not see that, and I don't think we should count on that. Okay. The third of 4 possible responses to climate change might be to remove greenhouse gases, in particular carbon dioxide, from the atmosphere and store it somewhere. This graph roughly displays a scenario of the future to the end of this century that's roughly in line with that optimistic scenario of the Intergovernmental Panel on Climate Change that I had a few slides ago. And you can see that the top of the sort of brownish red area slopes down. That's gross emissions. But then the lightly shaded area are negative emissions. And the black line is the sum of that positive and negative value. And you can see that around the year 2070 or so, in this scenario, the world enters net negative emissions, compensating for past emissions. This is an overshoot scenario, to use the lingo. How could this be done? There's a variety of proposals, 4, 5, or 6, depending on how you count them. Let me put 2 forward. One of these is to grow plants which pull carbon dioxide out of the air as they naturally grow, burn them to produce energy. You can capture the heat to some degree into steam, turn turbines, and generate electricity, but also capture the carbon dioxide that's emitted and store it underground or elsewhere. So this is bioenergy with carbon capture and storage. Has the double benefit of producing electricity with net negative emissions. This could also be done directly through the air, direct air capture. We could capture carbon dioxide out of the air and once again store it or perhaps reuse it. Now, of course, this is an energy-intensive process because carbon dioxide is quite diffuse in the air as it is. It's presently 405 or so parts per million. Nevertheless, prices for this are declining. There's a handful of private firms that are working toward commercializing this. The problem, there's a handful of challenges. One challenge is going back to this slide. If you look here, the presumed scale of negative emissions by the end of the century is around 15 gigatons per year. That's a lot. To give an order of magnitude, the largest thing that humans do with stuff is probably food production. And the best number I found for that is on the order of 4 gigatons per year. So this is assuming the growth of an industry by the end of the 24th century that moves stuff, mass, several times greater than global food production does now. My sense is that's not a wise assumption as we move into the future. To make this more challenging, the problem structure of carbon dioxide removal is more or less the same as cutting emissions. The benefits are distributed globally, the costs are borne locally. So you get the same international collective action problem. So let me move into the fourth response. Maybe we could cool the planet. And the idea for this is, the leading idea for this is inspired by large volcanic eruptions. This is Mount Pinatubo in the Philippines, which erupted in 1991. And the fine particles, primarily the sulfates that are emitted by volcanic eruptions, linger in the atmosphere, some of which go as high as the stratosphere, and they cool the planet by approximately 1 degree Celsius for about a year, depending on the eruption. So perhaps we could replicate this effect and inject an aerosol into the stratosphere. This could be sulfate. We're familiar with sulfate. We have natural evidence from that. Or it could be another method. This schematic here shows the use of a balloon, a tethered balloon to deliver. The latest thinking is that the best way to do it is through specialized aircraft. aircraft that can fly to the stratosphere and deliver something on the order, since you are engineers, you're probably curious, how much stuff do we need? Something on the order of about 5 megatons per year of sulfur. There's other methods. There's a couple of other proposals, although they don't seem to have quite the potential of stratospheric aerosol injection. I'll mention one other proposal. If seawater were sprayed into the lower atmosphere, 100 meters or whatever, as a fine mist, the water evaporates, leaving behind suspended fine salt particles. Those serve as cloud condensation nuclei. Clouds would then consist of a greater number of smaller particles, and they would be brighter. This appears to have the capacity to cool the planet by about 1 degree Celsius. It has limited potential. In the interest of time, I'm not going to dive into this slide, into the details. I'll only say that evidence consistently shows that a moderate use of solar geoengineering would return the climatic variables in which we are interested in closer to their pre-industrial values. Not only that, not just the means, but it would return the variance, the standard deviation, closer to the pre-industrial conditions. Red here is a global warming condition, and blue is the half solar geoengineering condition. And the 4 boxes are warming, extreme warming, precipitation minus evaporation, and extreme rainfall, extreme precipitation. Okay, so how can we think about solar geoengineering in its most important characteristics? Trying to step back, think abstractly in the way that I suggested about emissions reductions, negative emissions, and adaptation. Well, as I said, it appears to be effective. It also turns out to be fast. In this case, the planet can cool off on the time scale of months. We know this from volcanoes. It appears to be remarkably inexpensive in climate change economics, something on the order of 10 billion US dollars or euros per year to physically deliver the stuff into the atmosphere. Stratospheric aerosol injection is what I mean. There'd be other costs, of course, monitoring, compensation for harm, perhaps, etc. But the direct delivery costs are on that order. To give you a sense of what we're talking about, the annual cost of climate change impacts, as well as the annual cost of aggressive greenhouse gas emissions cuts, are on the order of 2, 3, or 4 trillion US dollars. So 100 times more than the direct costs of solar geoengineering. The climatic effects would be reversible, just like the cooling from volcanoes lasts about a year or 6 months, depending. This would also be, the direct climatic effects would largely be reversible. It's, of course, imperfect. It's imperfect for various reasons, such as the fact that greenhouse gases warm the planet differently than blocking incoming light would cool it. So there are legitimate concerns around regional residual climatic anomalies. And there's also issues like ocean acidification, which is caused by the carbon dioxide itself, not by the warming. CO2 dissolves in water, you get an acid, and this is harmful in particular to coral reefs. There's other possible environmental risks. The material in the stratosphere, for example, might accelerate the depletion of stratospheric ozone, or better put, it would slow down the recovery of stratospheric ozone, depending on the substance. There's a variety of social challenges, or perhaps socially mediated environmental risks. If this is so inexpensive and technically relatively simple, decision-making becomes an issue. Who decides on this? How do we ensure that it continues? Because if this were to suddenly stop for some reason, then the reversibility becomes a liability, it becomes a problem. All that pent-up global warming is going to bubble forth in the span of just a few years, and that would be highly dangerous. How can we responsibly research and develop and perhaps use solar geoengineering in a way that does not weaken our resolve to pursue the other 3 responses that I described earlier? Because in the long run, as I'll show, I think on the next slide, emissions cuts are essential. Just because they can't prevent climate change on their own Does not mean they are not essential. So governance in this is central. This is the area, the avenue in which I research, and I'm glad to talk about that on end. Oh yeah, the problem structure. How do these incentives play out? How can we describe this? Is this a global collective action problem, like emissions cuts and carbon dioxide removal? Well, as you can imagine, the global benefits are much greater than the global cost in sort of blunt economic terms, right? Foregone climate change versus costs of delivery. And in fact, it's so inexpensive that the local benefits to some countries, if we're interested in countries, in prevented climate change are great enough that it could financially justify that country undertaking solar geoengineering on its own, solely to reduce its own climate impacts, with the spillover effects of reducing climate change around the world. So the concern, though, then becomes, wait, not all countries are on the same page. Some might want more solar geoengineering, some might want less. Some might prefer the pre-industrial world climate. Some might want a little bit of warming. Some might be more risk averse and say, this sounds like an okay idea, but let's do another 10 years of research. So the concern is too much too soon, super optimality. The problem structure becomes one of mutual restraint. Even if hypothetically all the countries say this might be an option someday, those with the capacity to implement need to cooperate to the degree of saying, okay, let's stay in step and no one move ahead too fast, too soon. 5 minutes, thank you. But these 4 responses differ in not just their problem structure, but also in their timeline of effect and their capacities. So this graph is concentration. So in a way, it's the integral of emissions. It's also global warming or impacts. It's a schematic. So you can see that there's a business as usual scenario in which emissions go up and at some point in time slow down, or at least their rate of increase slows down. Emissions abatement can bend the line down, but it really can't give a negative slope because it's a cumulative problem. Carbon dioxide removal can not only bend the line down, but can yield a negative slope. But that takes a long time. So perhaps solar geoengineering has a role in this as a short-term risk management supplement, or better said, a complement to these other approaches to temporarily reduce the worst impacts of climate change, and then adaptation as well to shave off some rest. And then whatever is not addressed will be impacts on humans and the environment. This is, of course, idealized. The real world tends to be kind of sloppy. In terms of the engineering of solar geoengineering, I'm not an engineer. Most of you are. There's a common refrain that there's not enough engineering in solar geoengineering. There's a lot of climate scientists. There's a remarkable number of social scientists and humanities scholars involved in it, but there's stunningly few engineers. Doug McMartin is one of them, and he and climate and atmospheric scientist Kravitz recently published a review called The Engineering of Climate Engineering, saying that it would be, if implemented, it would be the world's largest engineering and control challenge. And they point to sort of 3 general categories of engineering questions. The first of which is the optimization of what they call aerosol optical depth, the intensity of solar geoengineering under static conditions. And they say, well, we've got a few degrees of freedom. It's not just one knob, so to speak. There's multiple knobs. Sure, you've got the overall amount. There's also a north-south hemisphere balance. And there's also, even more specifically, the distribution among the latitudes, because materials in the stratosphere drift toward the poles, and solar geoengineering is less effective at the poles. It's more effective at the equator. So it's not, it's fortunate that there are multiple degrees of freedom. There are, of course, temporal dynamics. There are seasons. There's climate change that's ongoing. how to optimize under these dynamic conditions. And then their third category of serious engineering questions is the issue of dynamic control, feedback to manage uncertainty. What happens if solar geoengineering is implemented and the world doesn't cool off as much as expected? Does that mean that decision makers should increase the solar geoengineering intensity? Or does that mean that it was just mere variability in the climate? Or maybe anthropogenic climate change is less severe than expected? Because there's the real risk that if you overreact, you could end up with excessive, super optimal solar geoengineering. Last slide, it wouldn't be a good talk without a little bit of self-promotion. It so happens that my book on the governance of solar geoengineering was released just a few weeks ago. I have a copy if you're interested in thumbing through it, and if you're interested in more information, links to buy it, et cetera, et cetera. It's on my website. Thank you very much.
Thank you. Thank you. I'll probably read your book. Would you say that the plight of the planet is so dire that we have the right or even the duty to take risks going into the unknown?
That's a very good question. I would characterize it that there is a chance that the risks are so dire that we should consider this seriously. Fortunately, the decision right now is not whether to use solar geoengineering, it's whether to increase research. Right now, the solar geoengineering research, by my back-of-the-envelope calculations, is 1% of 1% of climate change research spending worldwide. It's on that magnitude. Right now, I think there's a strong case for increasing research and moving towards outdoor experimentation of how do we get this stuff into the stratosphere? What would the chemical effects be in the atmosphere? Up until now, almost all research has been modeling.
Much of what you showed sounds like science fiction. So how much is actually going on regarding this shortage of engineers?
Well, to give you a sense, given the severity of climate change risks, and to me, the clear lack of capacity for emissions cuts to prevent dangerous climate change, there's remarkably little solar geoengineering research going on. Worldwide research spending is on the order of maybe $13 million. There's a handful of research groups around the world who do this somewhat seriously. I could count them on one hand. The first intentional outdoor explicit solar geoengineering research experiments are right now being planned, but have been planned for years. But they're proceeding extremely cautiously given the political sensitivity around
Are
this.
you too technical in your approach? I mean, you could plant trees, you could do the natural solutions instead.
Yeah. So natural climate solutions, such as planting trees and other forms of rewilding, soil management, one could characterize as a type of carbon dioxide removal. Less technical, more natural, and that should certainly be part of the solution. The unfortunate truth is the capacity, the total capacity for such things is really quite limited. A couple of gigatons total, I believe. And there's also questions of reversibility. If you plant trees, there's no guarantee that at one point in time those trees won't be harvested.
My Winnie the Pooh brain has come up with one idea about the role of engineers. We have to encourage them, and we have to restrain them.
Yeah.
So who and how should be encouraging the engineers to take up this huge task?
Well, I would think that right up until now there's been, I would consider, quite fruitful and healthy conversations among natural scientists, social scientists, and humanities scholars, and missing from this has been a critical mass of engineers. I think there's lots of opportunities for engineers to join in such an interdisciplinary dialogue and take it from there. I don't think I'm in a position to give specifics.
But these solutions are transboundary.
Yeah.
So is there a governance fitted for this today? The Paris Accord and the United Nations.
So the short answer is there is no international governance mechanism that is explicitly dedicated to saying this is how we're going to control this. In the long run, there needs to be. In the short run, there are some other rules and principles that I think provide a baseline of guidance to move forward into small-scale research and even larger-scale research that might have limited transboundary effects. Sure, in the long run, there needs to be international governance, and such conversations among political leaders are really just now getting started. There's a lot of ignorance in that domain.
We do have time for audience questions. If anyone, yes. You ready? And over there also, yeah.
So I was just wondering, there is a debate on in a small part of society on chemtrails and all of those sort of things. What do you think about the sort of people's response to injecting a lot of chemicals into the atmosphere?
Yeah. So public perception and public opinion around this is, in the long run, will be essential, perhaps the critical issue. It certainly pushes a lot of the wrong buttons, especially among those who are interested and concerned in environmental issues, particularly those in wealthier countries who take a more green perspective and less of a risk management and risk reduction perspective on environmental problems. Evidence, the public perception studies so far show mixed results, largely because people are largely ignorant of these ideas and how they might operate. And so the results tend to be very sensitive to how questions are worded and how information is presented. My quick takeaway is it's not out of the question that this is something that could be widely accepted or widely rejected. I could see both scenarios. And yeah, there's also the conspiracy theorist types who believe this is already going on, and I tell them it's not, but of course, there's no convincing some people.
One more question.
We have a question from Gunnar Wetterberg over here.
When you showed the slide with the volcano eruption, it struck me that this has already been tried before. I mean, how do you comment on the experience on what happened in 536 AD when the sun disappeared all over the world for at least some 3 years? We had almost no growth, according to the dendrologist, for some 10 years. Global temperature dropped by 3 degrees, and some of the consequences that the archaeologists can tell from that experience were catastrophic.
Thank you.
Including bubonic plague.
It's not your fault, Jesse, but maybe you could...
Right. So I think there's 2 takeaway messages from the fact that past very large volcanic eruptions have had quite disastrous effects. Not just in 536, there was, the name is escaping me, one in Indonesia in the so-called year without a summer, here in Europe in the 1600s, I believe. And I think there's 2 takeaway messages from that. Number 1, too much solar geoengineering could be very bad. So if we're going to err on the side of caution, that would imply a slow ramp up. A second issue goes back to the engineering question of dynamic control as a way of managing uncertainty. If we have a world of solar geoengineering, how should we respond to a volcanic eruption? It would need to be reduced, but how quickly and by how much, and how the response systems are integrated with measurements of of the expected impacts of such a volcano are highly relevant.
We talk about creative chaos, but how can you have this creative chaos when we have the sort of what I call the danger of extrapolation, the curves right up to 100 years ahead define what the problem is. Everyone will adapt to solutions to that problem, and in 5 years' time, it will show that it was completely the other way.
Yeah, yeah. I would encourage, to some degree, separating out the creativity and the chaos in this regard. I see climate change itself as the chaos. Climate change is a peculiar phenomena. I don't think humans have ever collectively tried to address such a long-term problem. And we're building models with a lot of uncertainty and with a lot of hidden assumptions about the way that complex systems are going to be functioning 200 years from now. And if you just imagine going back 200 years and say, well, what would have happened if, actually, it's a good occasion. This is the 100th anniversary of this institution. Even going back to 1919 and saying, well, let's build economic models based upon how we see the world. We in 1919 or 1819 see the world in 2019. And I suspect they would be quite incorrect. So there's this inherent uncertainty that needs to be recognized in climate change. That could go either way. Climate change impacts could be much less severe than we expect. They could also be much more severe. And it's that long tail of the probability distribution that most concerns me. And I see solar geoengineering as a risk management option that says, well, if we end up on that long tail, then we have a tool that we've developed the knowledge base for, that we could then implement if the need arises.
Thank you for this wonderful and scaring start of the morning, Jesse. It was lovely to have you here.
My pleasure. Thank you.